Hey everybody, welcome back. We are now looking at lecture number 5, where we talk about these things called residual plots, the standard deviation of the residuals, and this most mysterious thing called r squared. Essentially today it's all about evaluating whether or not a least squares regression line is appropriate to even use in the first place, and then to evaluate how good it is. So our EQ is basically just that. How can you determine if a linear model is appropriate, and how can you evaluate the quality of a linear model? So let's examine the following data set of radii for various pizzas and the area for each. Then we're going to calculate the residuals. Well, if we're calculating residuals, then we know we need to create a linear model for this. So I'm going to look at the radius and the area in inches squared for each of these pizzas. I'm going to put it into a two-variable statistics calculator that we see here. So I've already plugged all of my data into this. We have column A is our radius, column B is the area. If I go and click on scatterplot, I can see that this is clearly positive, and it looks really strong and really linear, to be honest. So I'm expecting a really strong correlation coefficient. Okay, now go back to statistics, take a look. We can see that the correlation coefficient is indeed positive and very strong, and we've got our regression equation y hat equals 42.314x minus 121.87. I'm going to rearrange that so it's in that a plus bx format that we would normally see. And here we see it. The predicted area is equal to negative 121.87 plus 42.314 times the radius, and this is all in inches. So now what we need to do is we need to find the predicted value, what the model predicts for every one of these, and we'll start to see just how reliable is our model. So the first one that we can look at is by plugging in 3 into our equation. Let's go ahead and do that. So my predicted area is 5.072 when I have a radius of 3 inches, so 5 inches squared. But the actual area is 28 inches. That seems really far off. What's the problem here? Well, let's go ahead and try and investigate a little bit further. We're going to calculate the residual. Just how far off is this? We remember that our residual is y minus y hat. It's the actual minus predicted. So when we calculate the residual, we will have 28, our actual area, minus the predicted area of 5.072 inches squared, and that's going to give us 22.928. That is my residual value. That's how far off the prediction is from a real pizza with this value. Now that seems pretty crazy. We had such a strong correlation. Why is this so far off? Well, let's look at all the other values and try and fill in each of the predicted values and the residual values. I'll go ahead and do this very quickly. So now you see the completed residual value table. What we can see here is that the next one was considerably closer. It was only off by about 4.5 inches, but now our model overestimated it. So that's interesting. And then we have several overestimates and then one more underestimate. But we get another one at the very end. That 22.573 residual value is another one that's really big. So what we want to try to do at this point is graph the residuals. We want to make what's known as the residual plot. The residual plot is going to show us how far off all of our predictions are, and we can start to see if there are any patterns. We'll start to see why patterns are going to be a really bad thing. So let's go ahead and graph this, where we will have on the x-axis the actual x value, the radius, but the y-axis is going to be the residual value. So this graph is what is known as the residual plot. It plots the actual x value against how far off each predictions are. So I'm drawing in these dots here just as a different color to make it stand out a little bit more. And do you notice a familiar shape here? What if we kind of connected these dots a little bit? I can see pretty clear shape here. What shape do you notice? this should look familiar from Algebra 2. This is a parabola. This is a quadratic relationship. But I thought we were supposed to be looking at linear relationships, and this had an extremely strong correlation coefficient. The correlation coefficient in this case was 0.9798. It was super duper strong. It was almost perfect. So why are we seeing this pattern here? Why are we seeing something that's quadratic? Well, stop to think about what our two variables were. Radius and area. The area, pizza is going to be a circle, right? And the area of a circle is pi r squared. It is not a linear relationship at all. It is a quadratic relationship. So it's no wonder that our residual plots actually show us a quadratic relationship. The residual plots, if you see a pattern with the residual plot, it's going to show you that your linear model is actually not really appropriate. A line should not be used to predict what's happening here. So even though something can look like it's super duper strong, it looks like it's linear, that's only for just a little bit. That's only for a tiny portion of that curve does it appear to be linear. After a certain point in time, it's not going to be linear at all anymore. And that's why we want to look at the residual plot. Even for things that look like they're strong, a linear model is not appropriate. So let's investigate a little bit more about these residual plots. The residual plot, we define it as a plot consisting of the points of residuals on the y-axis and the explanatory variable on the x-axis. A pattern in a residual plot indicates there may be unknown variables impacting the response, and a linear model is not appropriate. That ending part, that's really huge. Patterns are bad in a residual plot. Patterns tell us that that linear model, we shouldn't use it. We have to throw it away. Okay? So, what kind of patterns might you see? You might see what we saw here, some kind of curved pattern that indicates that maybe it's a quadratic relationship. You may see something that kind of goes down and up and down and up, or up and down and up and down. These are what we call periodic relationships. These would be using sine, cosine, or maybe even tangent to use as a model. Okay? Other ones that we might see, this is something where it starts off like we have really small residual values, stuff that's really close to the x-axis, small residual values 0, but then as we go further and further out, the residuals get farther away from the x-axis. We have bigger residual values, right? These are big residuals here. These are small residuals here. Okay? What does that tell me? Well, at the beginning, the model seems great. We have small residuals in the beginning. But at the end, we have very large residuals, and the model stops being very reliable at all. We call this a fan, because the residuals start to fan out from the x-axis on that residual plot. We could also see something that goes in the reverse direction, and it's like a funnel or a cone, right? And in a funnel, we start off with big residuals, and then as it progresses further, those dots start to get closer and closer to the line. So the further out we get, we end up getting more reliable. Okay? So with the fan, we have stuff that's reliable at the beginning and then less reliable at the end. With the funnel, we see stuff that is not very reliable at the beginning, but more reliable at the end. So what do we want to see? What we want to see is random scatter. We want to see random scatter around the x-axis of the residual plot, not in the scatter plot itself, not when we're actually making the least squares regression line. We want to look at the residual plot and see just dots littered in no discernible pattern. Now, the important thing for you to note is when you're looking at that residual plot, it should be very obvious. Patterns should be very obvious. One thing I see a lot of students do is they start to analyze that plot and they start to overextend what that pattern really looks like. Okay, so your pattern should be very, very obvious for you to start to say that your linear model is not appropriate. Okay? So looking at the scatter plot, seeing if it appears linear, and then looking at the residual plot to see if we notice any patterns. That's the first thing that we should do when we're wanting to evaluate the quality or appropriateness of the least squares regression line. There are other ways to evaluate the LSRL. Once we determine that the model is indeed appropriate, we want to see, well, how good is the model? And one thing we can do is look at the standard deviation of the residuals. So the standard deviation of the residuals, we denote that as S sub residuals, and we say that's the predicted value y hat will vary from the true value of y on average by this amount. And we get this formula that it's the sum of the residual square divided by n minus 2, and we take the square root, but guess what? We don't need that. I have never once calculated the residuals, the standard deviation of the residuals by hand. I've let a calculator do that for me. What's important is you being able to interpret it using a sentence starter or a template like what we have here. And this is just one way that you can do it, but I recommend using these in the beginning as you are starting to learn how to interpret these. So interpreting it, our prediction using the LSRL will typically be off by about S residuals, and you want to put that in context. So let's go ahead and look back at our truck example. Now from our truck example we looked at in the last couple of lectures is that the standard deviation of our residuals is $5,740.13. Okay, so if I wanted to write out this sentence in context, let me go ahead and do that. So the way I can interpret the standard deviation of the residuals very succinctly in context with an example we've been working with, the predicted price of a truck using the LSRO will typically be off by about $5,740.13. So what does that tell me? I know that my prediction is not always perfect. I know I'm never going to get it exactly dead on with the real price of a truck. So what can I expect to have vary by? I can expect by about $5,700. That's what the standard deviation of the residuals tells me. So I have a little bit of wiggle room that I should be paying attention to. And the bigger that standard deviation of the residuals, the worse our model is for making predictions, the less accurate it will be. So the point of that standard deviation of the residuals is it's a little bit better than looking at each individual residual and calculating all of them. It gives us a kind of a broad spectrum look at the residuals and the accuracy of our predictions. Okay, so this is just a more general way than looking at each residual. That's why we like it. Now, another thing is the coefficient of determination, and this is called R squared. This has been one of my biggest pet peeves and bugaboos in all of statistics when I was learning it as a student and as teaching it. It's a really difficult thing to understand. It's not very intuitive, but we'll give it a shot. So the coefficient of determination, R squared. Again, another gross formula that we don't need. I put it there so that way you can see it, just in case you are stuck without a calculator or something like that and you need to work with it. There you can find it. But a two-variable stats calculator is always going to give us R squared, so we don't really have to worry about that. Again, what we care about is the interpretation. The definition of R squared is the percent of the variation of the y values that can be explained by the least squares regression line. I don't know what that means. That's not an intuitive definition at all. Okay, interpreting it is not very much better anyway. It's the blank percent of the variation in the y variable can be explained by the linear model. Okay, what I'm going to do is I'm going to write out this interpretation just using this sentence starter, this template, and try and put it in context with the trucks, and we'll see if that's going to help it make a little more sense. So here it is, 66.4% of the variation in price of the trucks can be explained by the linear model. Now again, this is just something that I got from my two variable stats calculator when I went through and I plugged in all of our truck data from previous ones. So we're looking at the variation in price, and we're saying that a certain percentage of that variation in price can be explained by the linear model. Okay, well, what is the linear model talking about? It was talking about miles driven. So what we would say is that 66% of the change in value of a price can be explained by the miles on the truck. Well, what about the remaining percentage? That 33.6%, all of that is explained by other problems with these trucks. Were they in an accident? Did they get a sweet hookup with a nice tire lift kit and new suspension and a sweet audio sound system? Does it have like a crew cab that's got the DVD player and TVs in the back seat headrest? All those things are going to make the price change regardless of how many miles are on it. But what we are looking for is what is the biggest determining factor, hence our coefficient of determination. And with this, we found that the miles can help explain 66.4% of the variation in the truck. That's just based on the strength of the least squares regression line. The remaining 33.6% are all going to be explained by other unknown lurking variables. An important takeaway here is that the coefficient of determination r squared is a as in just one, and there are others, measure of how well your data fits that least squares regression line. Similar to the standard deviation of the residuals, it kind of tells us, is our model any good? Is it going to produce accurate results? Is it going to do it reliably? That's why we care about r squared. So now to summarize the key components of what we are trying to do today, how to evaluate an LSRL. A complete analysis of the appropriateness and effectiveness of using a linear model like an LSRL will include a discussion of, first, the appropriateness. Should we use one or not? We look at the residual plot. We say, do you have a pattern or not? We want no pattern, and we want random scatter around the x-axis of that residual plot. Then we look at the effectiveness. And to look at the effectiveness, we look at a couple of different things. We look at the standard deviation of the residuals. Why do we do that? It's to state how far off each prediction will be on average. We want a small standard deviation of the residuals. Then there's r squared, the coefficient of determination. It states how much of the variability in that response is explained by the linear model. We want a large r squared. We want closer to 100%, because then that says any change that we see in the price of our trucks or in the area of our pizza is due to our explanatory variable, the miles driven, or the radius of that pizza. Then we can look at the correlation coefficient, right? And that seems weird that it's the last thing that we really look at, but you have to do all of these other things first just to see, should you even look at that correlation coefficient. When we look at the correlation coefficient, again, to see, do we have a strong, weak, positive, or negative relationship? We want a moderate to moderately strong correlation coefficient if we are going to say that a least squares regression model is actually even good. Okay, so we're looking for anything from plus or minus 0.5 to plus or minus 0.1. Anything that's really considered weak, we would say, you know what, this is just not a very good model. It doesn't look like there's that much of a relationship between these two things. So that's it for trying to evaluate the appropriateness and effectiveness of a least squares regression line and how accurate your predictions will be by using that mathematical model. Thanks for watching. Have a wonderful day, and I will see you next time.